meters per second. Is that not right?
I was just checking it in their answers, but they didn't do it. They didn't give the numbers, so I'll check it. I think you got it correct, though, but I'll take a second to check. So 270 times 1,000 divided by 60 divided by 60, 75. Okay, we got that right. All right, so I'm going to actually put this here then. So we know that our initial velocity here is 75 meters per second. All right, I'm going to build that into the picture. We want to build as much information as we can into the picture. It's important to draw a nice big picture so you have room to put as much as possible in there. Okay, good. All right, this is an important habit for the whole course. You want to deal with unit problems as early as possible, because if you let them slide, it's easy to forget about them. So as soon as you see a unit problem, you want to make that conversion right off the beginning so you don't have to keep that in the back of your mind through the rest of the problem. So we drew the object's path, we labeled the initial and the final positions, and we've drawn velocity and acceleration vectors, so we're ready for step 2. So we can write down axes and positive directions. So we might, for example, say that our positive direction is to the right. That's conventional, and that's the most convenient thing to do here. We could have chosen left, but that would just make our life harder, so we might as well choose to the right. Yeah, this is to show, because when you're doing horizontal problems, you're usually focusing on the x-axis. Now, if you wanted to, you could also say the y-axis is like that, like this, but that's not really going to play a role in the problem, because we're not moving vertically. So we can just say that our positive x direction is to the right. So this is the conventional way to show that the positive x direction is to the right. So that's something that you always should write down so you don't forget it. Okay, so we've written that down, and we've included the positive direction over here. Now actually then, that tells us that we kind of made a little mistake here. Kind of a mistake. What's our initial velocity? Well, remember we've been talking about how it's important to put a sign in front of everything. So should that have been a positive or a negative? Yeah, at least if we choose this. So we want to get into that habit with all our numbers. So we'll call this positive 75 meters per second, once we've chosen this as our positive direction. So that's our step 2. Okay. Step 3 is to break things into components. That's only necessary for 2-dimensional problems. So we'll see that next week. For a 1-dimensional problem, we don't need to break things into components. So that's there on the handout. All right, now here's the very important part of being systematic. We need to write down the kinematics variables. You've probably already seen those in class, but you're reminded of what they are up here. If this was a 2-dimensional problem, we'd have to write down all 10 of them. But because this is only a 1-dimensional problem, we only need to write down 5 of them, the 5 for the x variables.
And because we're going horizontally, we use x.
That's right. Just because that's conventional. So what are our variables? They are delta x, v initial x, v final x, a sub x, and t. All right, now technically speaking, since we're only dealing with the x-axis here, a lot of people would just leave out some of these subscripts. They would say, well, I know I'm dealing with the x-axis, so why put in all those x's? So they would just write the variables like this. But in next week, you're going to be doing 2-dimensional problems where you're going to have both x and y axes. So we might as well get into the habit of reminding ourselves that we're only focusing on the x velocities, and we're only focusing on the x acceleration. Everything here is on the x-axis. Time doesn't have an axis, but everything else I'm going to put down in x. That'll help us when we're doing 2-dimensional motion next time. Okay, so here's all the variables. These are the 5 variables, so these really should be memorized, so you can quickly write those down. So the key thing, you should actually physically write these down for any kinematics problem. You don't want to just keep reviewing them in your head, because 5 is too much to keep reviewing. All right, so we've written those down. If this was a 2-dimensional problem, we would also write down all 5 for the y variables, but here we only need these. Now, underneath the variables, write down the given values, including signs, and indicate the question. So do we know which of these the question is asking us for, or do we know which of these we have a number for? Let's start writing down some numbers of the question.
Okay, we know the initial, so that's 75.
Right, except better to say positive 75 meters per second. Good.
The final is 0.
That's right. If we hadn't already figured that out, this would now be the time where we have to figure that out.
Okay. We don't know delta x. That's what we want to find, right?
That's right. So let's put in a question mark for that. It's a very good habit in physics. One thing we're going to try to get into the habit throughout the whole course is, as early as possible, we want to identify what variable we're trying to solve for and label that with a question mark. So now we've labeled that with a question mark. Maybe we should have built that into our picture as well. We should have told ourselves what we're trying to figure out. So this is what we're trying to figure out. It's good to build as much as possible into the picture. All right, now go back and let's take another look at the problem. Hopefully they told us something about one of these two variables. So let's take another look at the problem and see if they gave us any help with
So
those
they
two.
give us an acceleration. It says
Good.
at 4.5 meters per second squared.
Good. So what should I write down here?
4.5 meters plus 4.5 meters per second squared. Well, wait a second. Because it says the plane then decelerates, i.e. undergoes acceleration directed opposite its velocity.
Right.
So
Good.
then it should be negative 4.5.
Okay, well you just avoided the biggest trap on this problem, so that's good. And this is the kind of trap that tends to appear on the exams. So this is the thing. This is what I meant when I said that we have to be super conscious of the signs. Most people don't even think about the sign here, but if we're thinking about the signs, then we can catch these types of traps. Now, technically, how do we know that this is negative? Well, we've actually, you can see that just when we've written down, what direction is the acceleration in? Left, right, up, or down?
Left.
And what direction is our positive direction?
Right.
We just chose that. Well, if right is positive, then left is negative. That's how we know that this has to be a negative. It's not just because it's decelerating. A deceleration could represent a positive number if it was in the positive direction. If suppose we had chosen this to be the positive direction, well then the velocity would be negative. And the acceleration would be positive. Who's positive and who's negative just depends on who you choose as your positive direction. Now this is a much better choice because I think it's much more commonsensical. But you don't want to think that deceleration always means negative. The reason this is negative is because the acceleration is to the left and our positive direction was to the right. And you figure that out. Okay? All right. All right, so this is why I was recommending before always to put a sign in front of displacement, velocity, and acceleration, because otherwise we're likely to fall into these traps. We don't need to put a sign in front of time because that's always positive. But the other things we always have to think about whether they're positive or negative. Okay, so there we go. Now they didn't tell us the time.
So right now we have 2 unknowns.
Technically, that's right. Yeah, you're right. We have 2 unknowns. Only one of the unknowns is something that the question cares about. But you're right. There's 2 things that we don't know. Now, let's see, where are we? Step 4. We wrote down the kinematics variables. We wrote down the values. We included the signs. We indicated the question with the question mark. We used consistent units. Now, step 3, when are we ready to start doing math? We only need values for 3 of the variables. All right, so it doesn't bother us that we don't know the time.
Is that true for when it's 2-dimensional too?
Yeah, that'll be true for 2-dimensional motion as well. Yeah, we'll see in more detail how that works next week. But yeah, so this whole method here, hopefully it's going to work for both 1 and 2-dimensional. We're going to try to use the same handout for both 1 and 2-dimensional motion. All right, so this is a very important idea. We need 3 numbers, but we don't need 4 numbers. So in fact, in almost all of these problems, they usually don't give you superfluous information. So in most of these problems, you're right, there's going to be an extra unknown. But we can't let that bother us. We don't need to know this.
But sometimes they might give you superfluous information just very often.
Occasionally, yeah, that's right. Okay, but here we have 3 of the variables. So now we're ready to choose a kinematics equation. And I guess you don't, maybe it's not really necessary to memorize those equations. You can just put those in the cheat sheet. So I just put those here. Now, how do we pick out the right equation? Here's the fastest approach. Each of the equations is missing 1 variable. Each of the equations is missing 1 of the 5 kinematics variables. For example, this equation doesn't include delta x, and this equation doesn't include the acceleration. Well, then we want to pick the equation that's missing the variable that we weren't given any information about in the problem. So we want to pick the equation here that's missing time.
So that third one.
That's right. So let's just write that down.
Wait, we want to pick it because it's missing time because we don't care about time in this case.
That's right. We have no information about time, and we're not being asked about the time. So we don't. It wouldn't make sense to have an so if we have to pick an equation that's missing something, we want the equation that's missing the time. We don't want we don't want an equation that's missing any of these because then we wouldn't be able to plug these in. And we don't want an equation that's missing this because then it can't tell us what the delta x is. Yeah, that's right. So let me put it the other way. We need an equation that includes the things we know the numbers for and that includes the thing that the question was about. But rather than searching for all four of these, the shortcut is just to search for the equation that doesn't include this. That just helps you to save time and pick out the right equation.